And now it's 10, and let me introduce our attendees to you, Bulent. Some of them may remember you because you were here in Madison visiting with me 4.5 years ago, and you gave a lecture similar to the one you're going to give now. It happened to be a very particular day, and as having been educated in Canada, I wasn't aware that it was Columbus Day. The same day in Canada is Canadian Thanksgiving, and it was a Monday morning, and we went to the bank, and the bank was closed. And we were kind of worried as to how we would deal with the situation. I was going to invite everyone back to my house, and we were going to set up the projector in my basement when suddenly somebody found a window cleaner cleaning the bank, and he was kind enough to open the doors, and we started an hour late, but you still managed to get in a wonderful lecture. And I was reviewing your slides recently, and I'm glad that you will be reviewing some of those this morning, because probably of the people I see on the list, probably less than a third were present that day. So I'm sure that we'll all be glad to review some of those slides this morning. And just to refresh everybody's memory, Bulent Atalay is an old friend of mine I met on a cruise ship 5 years ago or so. He's a theoretical nuclear physicist, the author of numerous technical articles in physics, and he's been a professor of physics for 4 decades at the University of Mary Washington, an adjunct professor at the University of Virginia, and a member of the Institute for Advanced Study at Princeton. And he lectures around the world on his expertise in the A subjects, as he calls them, being art, archaeology, astrophysics, atomic physics, and Ataturk, while claiming little knowledge of the B subjects, such as business, banking, and biology. So we are delighted to have you back again, Bulent, and you have the slides and the mic.
All right, I see you, and I think Louise's screen. I'll go to the share screen, or should I go now, or
yeah,
wait?
Sure. At your convenience.
Okay.
Now it's good.
Okay, I see where we are.
This is being recorded, so we can. Sometimes
right.
This will be up in a week or so, where people who would like to look at the slides again and hear you give a talk can do that.
All right, well, it's a pleasure to be here again. Actually, it's nice to be home and doing this across the country like this.
Yeah.
I remember as we flew into Madison shortly before the debates in 2016, a man sitting next to us on the airplane saying, this is 100 square miles of liberal territory surrounded by a sea of reasonable conservatives.
We've heard that in various ways, yes.
Yes. Indeed. Well, I know you have a governor who's not very fond of science. And not a governor, no, not governor. I meant Senator Ron Johnson.
Yes.
Yes. You know, we became modern, according to historians, with the Enlightenment. And the very first event in the Enlightenment is Isaac Newton's magnificent book, The Principia, the Mathematical Principles of Natural Philosophy, published in 1687, which starts the Enlightenment. Although he was an extremely religious man, he essentially told us that demonstrated that the universe was mathematical. We could understand the universe. We didn't have to blame, give credit to the divine and blame the devil for his handiworks. It was all understandable. Well, science has obviously come a very long way. Although nowadays there seems to be a little bit of a kickback against this. In this room, we had a visitor last year, and he tried to he said, "There's no global warming, is there?" And I said, "Yeah, unfortunately there is. There's global weather change." And he said, "Can you prove it?" And I said, "It's not that I can prove it, but Oxford University has this, the physics department published this data recently showing 150 years of global weather temperature change. And indeed, there was an exponential rise during the 150 years that we've had heavy industry and ocean crossing steamboats using fossil fuels. Then he wanted to discredit science in evolution. And I said, as we see, we have a universe of 13.7 billion years, and we can understand it pretty well mathematically. Religion and science and physics can certainly coexist, but they have different magisteria. They don't answer the same questions. So anyway, let me start showing some slides, and this will dictate the flow of the discussion. Now, this is a somewhat dated graph or table, but it shows how energy consumption goes in a home. It's dated, it's probably published in the 90s. There wasn't heavy computer use, but computers are actually very efficient. So these numbers would not have changed very much. Space heating takes the large bulk of the electricity that we use in a home, 55.4%. And most of these numbers are, I think, quite reasonable even now. As for sources of energy, this table, again, it's old, but none of these numbers have changed, either in BTUs per ton or joules per kilogram, which is used more by physicists. Burning coal, bituminous or anthracite. As I move my cursor around, do you see it?
Yes, yes, we do.
Oh, okay. So 29 million joules per kilogram is the energy content of coal. Lignite is a little bit less, about 2.5 times less. Peat, again, it's of the order of 10 to the 6 or 1 million joules per kilogram. You go down the list, natural gas is more efficient, 10 to the 6. Hydrogen gas, even more so, 10 to the 124 times 10 to the 6. The list includes dung, assorted garbage and trash, bread, butter. They're all of the order of 1 million with a coefficient in front, 33, 10, 12, etc. Then you go to fission, suddenly it jumps up by a factor of 10 million times as much energy per kilogram. This is for fission, 8 times 10 to the 13, 5.8 times 10 to the 11. For deuteron fusion, it jumps up another factor of 1,000, 3.3 times 10 to the 14. This is for 7 MeV per deuteron a pair of fusion. We'll look at all this and see why it's so difficult to achieve and why it's so essential to seek anyway. With deuteron tritium fusion, DT fusion, the number is 9.7 times 10 to the 13. The very last number is total mass energy conversion. That's called annihilation, pair annihilation. If an electron meets a positron, that's an antimatter electron, they completely destroy each other, and you get a whopping 9 times 10 to the 16 joules per kilogram of energy. It's just E equals mc square, where the mass of the electron pair is annihilated. Unfortunately, in physics, there's always this fear that we're supplying fudge factors. The favorite cartoon from Sidney Harris, I think you should be more explicit here. There's an element right here that we often fear. Einstein did the same thing when he first published general relativity in 1915. And his equations suggested that the universe was actually growing, and he didn't believe it. He believed in a static universe, and he supplied a fudge factor, a lambda, a large capital lambda, which was a fudge factor. But then some years later, when it was shown that the universe was in fact expanding, then he changed his mind and he said, it was the biggest mistake of my life. I should have simply accepted the mathematics, the mathematical results. Nuclear physics starts with Henri Becquerel and his 2 assistants, Marie Curie and Pierre Curie. Marie and Pierre met at the lab, Becquerel's lab. It was a serendipitous experiment that revealed there was energy beyond what we thought was phosphorescence energy. That is, certain phosphorescent materials, when you subject them to sunlight and then put them in the dark, they glow. In this case, with pitch blende, there was no need to put sunlight activate the phosphorescence. It glowed all the time. Now, the serendipity came when it was a weekend. They were going to do an experiment on a Saturday or Sunday. There was a photographic film plate. There was a lump of a clump, actually, of pitch blende. The film was wrapped in heavy tar paper, and the pitch blende was placed right on top of the photographic paper. There happened to be a brass cross in the way of the pitch blende and the photographic plate. On the Saturday, Becquerel came to work, but his assistants didn't, so he postponed the experiment. He didn't have a chance to irradiate the pitch blende, but Sunday, when he didn't come to work, but his assistants came, they assumed that the experiment had already been done. They processed the film plate, and sure enough, they discovered that in the film plate, there was exposure left over from the pitch blende, and that cross, the brass cross that was in the way, had a distinct impression. Then they realized there really was something very strange about this material. The radiation was inherent. Marie Curie and Pierre shared half the prize, and Henri Becquerel received the other half. But then, that was in 1903, but in 1911, Marie Curie won a Nobel Prize for chemistry by herself in identifying a couple of elements. Now, curium is named after her. Around the same time, within a year, J.J. Thomson at Cambridge University discovered the electron. He did what's called the charge to mass ratio experiment, and he found that, in fact, the electron itself was a lump, that it wasn't just a stream of continuous radiation, but it was a particle in a sense. By consensus, the greatest experimental nuclear physicist ever is Lord Ernest Rutherford, who around 1911 performed an experiment. He wanted to find the nature of the atom. Now, what J.J. Thomson had determined was there was in fact an atom, there was an electron, but the electrons were embedded in the positive wad of wad, the proton in a sense, and the atom appeared neutral. What Lord Rutherford did was bombard gold foil with alpha particles, and he found that the alpha particles scattered at dramatic angles. This suggested that the atom was in fact was largely localized with a very heavy nucleus and very light gnat-like electrons orbiting it. His assistant, graduate student, Niels Bohr, did the first theoretical analysis of the hydrogen atom. But then, within 10 years, the quantum theorists, the quantum mechanics came in. Now, this is maybe the most memorable photograph of physicists ever taken. The photograph was taken in 1927 in Brussels at the Solvay conference. There are 29 individuals in the picture, and 19 of them were either won the Nobel Prize or already had the Nobel Prize. The front row represents the old school, the Old Testament of physics. And in the back is the new school. Niels Bohr, right here, first from the right at the far right, actually in the second row. If you can see my cursor, was a Danish physicist and the assistant to Rutherford. He was sort of the godfather of quantum mechanics, proposed by Heisenberg, Schrödinger, and maybe the star of the group, the understated star, Paul Adrien Maurice Dirac, right here. A man of very few words, but rarely wrong. He gave us the mathematics of quantum mechanics. In the picture are Planck, who had discovered in 1900 that radiation came in lumps. Einstein, who proposed in the photoelectric effect that light could have either a particle nature or wave nature. It's called a dual nature, an argument that had been going on for 200 years, essentially, was resolved. Newton had suggested light consisted of particles. Young in the 19th century suggested light consisted of waves only, but Einstein showed that it had a dual nature. Now, this young man here in the back, Louis de Broglie, he was a French prince. He submitted a PhD thesis at the Sorbonne, and he suggested in 1924 that particles, as we know them, electrons, protons, atoms, also had a dual nature. They could behave like particles or waves. Now, no one really knew how to evaluate this thesis. The head of the physics department, Langevin, sitting right in front, said, we can accept it, but if it's wrong, we'll fall flat on our faces. After all, he is a prince, and we should be very careful with his assessment. But Einstein was passing through town, and Langevin asked him, He said, is there a way you can help us with this? Of course, we know how to handle it, but your opinion would be really valuable here. Well, Einstein didn't know what to do. He said, let me sleep on it. The next morning, he came back haggard. He said, there might just be something to this. Give me some more time. He sent the paper to his old friend Dubai, seated, I believe, at the far left on the left. And he said to Dubai, is there anyone in your department who can evaluate this? This was at the Swiss school for where he had done his PhD. And Dubai turned around and gave the problem to Schrödinger. He said, you're up for tenure. Tell us in 2 weeks at the next physics meeting whether there's anything to this thesis. And he said, I don't understand what kind of wave theory this is. There are no equations here. See if you can write some equations. Well, Schrödinger wasn't keen on doing this, but it was the head of the department asking him. He was up for tenure. So he went to a Swiss chalet with his wife, and 2 weeks later came up with an equation. And the equations were sent by telegram to Einstein. And Einstein wrote to Langevin. He said, give the boy his PhD. He can't do any damage with a PhD in physics. And that was, in a sense, the beginning of the end, because within 1 year, Schrödinger had published the wave theory of quantum mechanics. Heisenberg had published the matrix theory of quantum mechanics with the uncertainty principle. And Dirac, within a couple of years, had essentially shown that the two theories were equivalent. Quantum mechanics is now seen as the greatest scientific theory in history. But as the master Niels Bohr said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it. Well, in 4 decades, I think I understand it, but I'm not sure. Okay, now, everybody who has even a high school education knows about the periodic table of elements. This number is quite right. There are 114 elements that have been identified. The lanthanum series would fit here, and the actinium series would fit here. The sum total would be 114. Now, in the next slide, astrophysicists. Among astrophysicists, there's a field called nucleosynthesis of the periodic table, how the elements came about in the first place. According to quantum mechanics and the standard model of elementary particles, hydrogen and helium were created in the Big Bang. At least the particles that make up hydrogen, meaning the proton and the electron, and helium, the proton and neutron and the electrons going around them. It takes 2 protons and 2 neutrons to make a helium. These came very early in the Big Bang, 13.7 billion years ago. Now, notice some of the other elements. The green in the periodic table, they were created in the dying of low mass stars. The red ones, cosmic ray fission, merging neutron stars. Some of these happened billions of years later than the 13.7 billion years that started the universe. So now take a look at the following. I have a red dot over hydrogen. These 4 elements comprise 98% of our bodies. Hydrogen, carbon, nitrogen, and oxygen. The other 2% are comprised by these elements: phosphorus, potassium, sodium, chlorine, and magnesium. this actually gives you 99.9% of all the elements in the human body. But isn't it remarkable that they were produced at different times? So we're not created with all our atoms of exactly the same age. The hydrogen was created in the Big Bang in the very beginning from the primordial soup, sometimes called the, well, it is called the primordial soup, or the quark soup, made up of quarks and electrons. And then as it cooled off, the other elements came to pass. One of my favorite figures in physics is Maria Geppert-Mayer. She was born in 1906 in what would be Czechoslovakia now. She married Meyer, a German physicist. They came to the United States in the 1950s. Behind her, you can see part of the periodic, not the periodic table, but the chart of nuclides. Now, this chart is comprised of a large, oh, I'm going to go back one, sorry. In this, there's a large segment right here. It looks like a large banana. It sits on top of this middle segment, and then that sits on top of this segment. That multiplies the boxes on the periodic table to 1,500. This is quite astonishing. You're looking at only about 150 boxes, but among these boxes, you see hydrogen down here is comprised of 3 isotopes. What that means is there's a proton and an electron orbiting it. There's a proton and a neutron. That makes it the deuterium atom, or the deuteron nucleus, and tritium, this H3 right here. It's radioactive. It has a half-life of about 12 years. Helium 3, helium 4, helium 6, and helium 8 accounts for the helium atoms, but only 2 of them are stable. Then lithium, beryllium, boron. Well, this table is largely due to Maria Geppert-Mayer and Jensen, who published the theory of nuclear shells. Just like electrons have closed shells of electrons, the atoms do, the nucleus has closed shells of protons and neutrons. The one element I wanted to point out here, the vertical axis here is the atomic number, or the number of protons. The horizontal axis is the number of neutrons. The one element I wanted to point out, because everyone is familiar with it, is carbon-14. Carbon-14 is, we have carbon-14 in our bones, along with stable carbon-14, non-radioactive. We have a tiny amount of radioactive carbon-14, which has a half-life of 5,730 years. All of us, while we're living, has the same amount. We have 0.007 microcuries of carbon-14. But once we pass away and we no longer ingest food and breathe oxygen and nitrogen, this clock begins to run down. In 5,730 years, it's down to a half. So instead of 3.7, instead of 0.007 microcuries, there will be half as much after 5,700 years. After another 5,700 years, it'll be down to 1/4, and then 1/8, then 1/16. And you can tell up to about 50,000 years how old a living specimen was at the time it died. Uh, Inside the nucleus, we know of four forces of nature. There's gravitation, there's the electromagnetic force, there's the strong nuclear force, and there's the weak nuclear force. But within the nucleus, the strong nuclear force accounts for almost all of the force. So even though protons repel each other, within a nucleus, they're still bonded. There's a simple analysis you can make with one particle. Now, the particles, I'm not distinguishing between the proton and the neutron. This is the nucleon, generic for a proton or neutron. It has no bond because it's alone. With two particles, it could be the helium atom, but with or the deuteron atom, there is one bond. Between three particles, there are three bonds. It's like asking the question, if you're toasting people at a party, how many clinks can you get? Well, three people, you can get only three clinks. Here, here, and here. Between four people, you can get 1, 2, 3, 4, 5, 6 clinks. That's the number of bonds. With 5 particles, with 6 particles, it's actually quite easy in a branch of mathematics called combinatorics. How many bonds there will be? And the equation is right here. It's 1/2 a times a minus 1. So if there are indeed 5 particles, 5 times 1 less than 5, that's 4. 5 times 4 is 20. Divided by 2 is 10. There'll be 10 bonds. With 6 particles, it would be 6 times 5, that's 30. Divided by 2, 15 bonds. For 236 particles, I used a calculator and found that there should be 27,000 bonds. Why 236? Well, when uranium-235 fissions, it absorbs the neutron and becomes 236, and this becomes immediately an issue, the number of bonds. Okay. These are just the equations from the analysis of how many bonds there are. The average binding energy between all of these bonds should be the total binding energy divided by the particle. This happens to be the equation of a straight line. So you expect the average binding energy in the atomic nucleus to increase linearly like this. This is a straight line. This is what you expect for the binding energy of the atomic nucleus. But what the experimentalists determined in the 1940s, 30s rather, is that it's a much more complicated binding energy. It initially goes up linearly, just like this, straight line, but then it oscillates. It reaches a plateau, and then it starts coming down like this. When you get to heavy particles, heavy atoms, like uranium-235, the total binding energy is a little bit less than the peak of the plateau. In nuclear fission, let me turn this curve upside down. In nuclear fission, you essentially have a uranium atom consisting of 235 nucleons absorbing a neutron and breaking up, each particle giving approximately 1 MeV of energy. That's right here. So about 200, since there are 236 particles, roughly 1 of the 200 MeV, or 1 MeV per fission, is what a normal fission reactor gives off. It was discovered in 1938, 1939, just about as the war started in Europe. Otto Hahn and his assistant Lisa Meitner did an experiment. If uranium-235 absorbs a neutron, it becomes uranium-236, but then it breaks up into a pair of elements. They could be barium and krypton, but they don't need to be. They could be xenon here, they could be rubidium here. The number 56 and 36 have to add up to 96, which was the original number of protons. These are fission fragments. There's a probability for different configurations or different pathways. 57 and 35, 58 and 34. That would be lanthanum, I think, or barium. Those are different pathways. 200 MeV of energy plus 3 or so neutrons. If you take careful statistics, it turns out to be 2.47 or so. That means out of 100 experiments, you'll get 247 straggling neutrons. So the original neutron comes in, breaks up the nucleus into 2 fragments, and there will be 2 or 3 more neutrons coming out. They will strike other uranium-238 235 atoms, which will participate in which will multiply just like chainmail. And in the first reactors designed, there were the fuel rods. You can see those are the bars, the 4 bars here, and there are the control rods made up of boron, essentially, which mop up the extra neutrons. You want to be able to sustain the reaction with mopping up 1.5 of the neutrons while letting 1 neutron from each of the other 2.5 cause further reaction, further splitting.
Could you advance your slide one more time, Bulent?
I'm sorry?
Could you advance the one more slide?
Oh, I'm sorry. Oh, thank you. Very good.
Okay.
Yes,
Okay,
I was looking at the wrong slide.
Right.
So in the boiling water reactor, you had the fuel rods, 1, 2, 3, 4 here, stylized, and the control rods made up of boron absorbing the extra neutrons. If you don't have the control rods, you would have a meltdown. There are different ways of, you have to slow down the neutrons, otherwise the uranium-235 doesn't absorb them. This is called thermalizing them. The neutrons have to be traveling about 2,500 meters per second, 5,500 meters per second to be absorbed. If they're going too fast, the rods will be transparent to them, so you have to thermalize them. And you thermalize them either with heavy water or with graphite. The Russians in Chernobyl made a great mistake when they made their reactors with graphite and they had the meltdown. In any event, the water heats up, it boils, it runs through the turbine. The rest of the physics is very simple. It goes back to Faraday's circuital law. The turbine turns the generator. Mechanical energy is turned into electrical energy, and the spent steam is circulated back through the pump into the reactor. You need the cooling water to cool down the water to pump back into the reactor. The downside of this design is that the turbine becomes radioactive in time, as do the pipes, and the boiling water reactors no longer exist. The pressure water reactor has one more stage where the radioactive water is completely contained in here, The turbine, an expensive piece of machinery, is no longer in touch with the radioactive water because there's a vat of water being turned into steam here to run the turbine. And then the rest of the reaction, of course, rest of the mechanism is the turbine turning the generator and generating electricity. Everything is the same. In a liquid metal fast breeder reactor, what you would have, now there are only 3 nuclides, that's the generic word for all those isotopes, isotones, isobars, etc. There are only 3 known nuclides that can fission: uranium-235, uranium-233, and plutonium, 239. Now, they don't exist naturally, but if you take thorium-232 and make a blanket of thorium-232 around the reactor, then the neutrons from the reaction will convert that the thorium-232 to uranium-233, which will make that a fissile fuel. Or if you have in here, let's see, plutonium, if you have uranium-238, uranium-238 is fertile, but it's not fissile. It doesn't divide up. But uranium-238 can absorb neutrons and decay into plutonium-239, and then it becomes a fissile fuel again. And this was understood in terms of the physics in the 30s, but not really made into reactors till much later on. There's a simple cycle that you can follow where the thorium-233 is made into uranium-233. So the fertile nucleus becomes a fissile nucleus. I think we talked about this very briefly, Richard, some time ago, but a safe type of reactor, fission reactor, would be the modular high temperature reactor, where the pellets of uranium would be kept at a distance from each other, never giving rise to a super criticality, by having these glass spheres. The glass spheres are 6 centimeters or 2.5 inches in diameter. They're embedded with the uranium oxide fuel. They're in the fuel rods, essentially in the reactor. Gas is circulated by pumping down like this. Doesn't come into contact with any turbines, except here there's a heat exchanger and you again generate electricity. It's an expensive but a safe reactor. Okay, I won't go into the nuclear waste problem. Is a problem because the Congress has never settled once and for all how to store the radioactive waste. The salt mines, the Yucca salt mines, I believe in Nevada would be a safe way to do it, embedded in synrock or synthetic ceramic with the waste. But at this juncture, radioactive waste is still kept in large pools at the individual reactors. Now, I found this data online comparing the number of fatalities in mining coal compared to mining, generating the electricity. Certainly, nuclear is far safer than any of the other sources, certainly much, much, much safer than fossil fuels. There again is that that binding energy curve with the fission yield 1 MeV per fission product. Now, the pioneers of nuclear physics, nuclear fusion, Lyman Spitzer at Princeton, essentially the mastermind of the the fusion plants at the Princeton program, the plasma physics lab, came up with these reactions, explained the reactions where deuteron and deuteron fuse to give you hydrogen 3, that's a tritium nucleus, plus 4 MeV of energy, 2 deuterons giving helium 3, 3.3 MeV. Once the helium 3 exists in the fuel, then it can combine with the deuterium. And once the tritium exists in the fuel, it's been created up there, it can combine with the deuterium. Now, it's much easier to see these reactions as D's and T's. Deuteron-deuteron reaction gives 4 MeV of energy. If it combines into helium-3, 3.3 MeV of energy. And then, just like a series of mathematical equations where these arrows represent equalities, you could sum up everything on the left and everything on the right. You would wind up with 6 deuterons, and on the right-hand side of the equation, 43.2 MeV of energy split up between 6 deuterons, or 7 MeV of energy. That compared to the 1 MeV in fission. So there's a great deal more energy in fusion. Now, the fusion reactor, this is a stylized version of it, with tritium as the fuel and deuterium as the fuel, would be kept in vats, mixed and injected into a tokamak. The tokamak, incidentally, is the Russian acronym for a donut-shaped machine. I meant to bring a donut with me, but forgot. This is the cross-section of the donut. The injector mixes the tritium and deuterium in equal parts, keeps it with superconducting magnets confined. It has to raise the plasma. Plasma is highly ionized gas, and the particular reaction, again, deuterium, deuteron, tritium, triton, giving 17.6 MeV of energy. Meanwhile, the lithium in the second shell, picking up neutrons, becomes lithium-3, breaks up into tritium and alpha. What that means is this is not only a breeder reactor, but it's also a power reactor, because there's new tritium coming into the tritium tanks as the byproduct of the process. Now, in 1989, we were all surprised when 2 chemists in Utah published papers about how they had achieved cold fusion. Well, hot fusion calls for 100 million degrees. That's 6 times hotter than the center of the sun. But cold fusion here was about 1600 degrees of heat, and everyone was thrown into bewilderment, and it turned out that what they were picking up as neutrons was radon in the lab, and there was no case for cold fusion. So back to hot fusion. This is the machine that I knew at Princeton, the tokamak the TFTR, tokamak fusion test reactor. It actually achieved temperatures well beyond what you need, but there are three factors that must be satisfied. It's the temperature, the confinement time, and the time of the duration of confinement. In the 1990s, unfortunately, this was during the Clinton era, a Congress came into power with more social-minded than science-minded, and they cut off funding for the tokamak in Princeton, and many fusion plasma physicists from Princeton and elsewhere went off to Europe. But here is the JET machine in England, the Joint European Tokamak, and you're looking at the color of 100 million degrees there. It has no color. The ITER project, the International Thermonuclear Experimental Reactor, about, I think, 78 kilometers from Marseille, is being built now. And there is the scaled up version of the Princeton reactor. Usually you'll have a person or two put into the picture for scale, and there you can see the size of the tokamak. In 2025, in just 4 or 5 years, I don't know how much the pandemic has slowed the plans down by, but by 2025, they expect to break even. This is the experimental site and the reactor under construction. This picture was projected in 2016, and hopefully by 2025, this is what we'll see. Again, there are a few humans in the picture for scale purposes. There's 1 year and 1 year. In the reactor, there are normally 2 types of magnetic coils. One is the poloidal coil that goes all the way around the donut, and it's to constrict the gases, the plasma, this way. Then there is the toroidal that goes around the minor diameter of the donut. So the toroidal goes this way, the poloidal around the entire donut. And the heating is done by essentially 4 different technologies. One of them is with constriction. Another is by passing electricity, a current through it. And just as a wire heats up when you send a current through it, well, there would be heating due to current being sent into the gas. There would also be radio frequency or RF heating. And in distinction to those, in the Nottingham Power Station in England, Nottingham is right here, they're hoping by 2040 to actually have a more miniaturized version of the ITER project. And this is their proposal. In any case, by 2040, the best estimate for actually joining the grid. Although there is this is something that Richard sent me information on, and then I did some research. The spark reactor a young man, let me see, by the name of Brandon Sorbonne, sort of like an Elon Musk with great vision. He got funding for his CFS project. This is the Commonwealth Fusion Systems project from Bill Gates, Jeff Bezos, Richard Branson, visionary businessmen. And it's a more compact device, but mathematically, by improving the magnets, you should be able to combine the gases and get those criteria of temperature, confinement time, and fuel pressure. We go back to the beginning, and it all starts with Einstein's E equals mc squared. But I will stop right there. My hour is up. I guess I can stop sharing now, unless we have to go back to the slides.
Yeah, we're not rigid about the hour, Bulent, but that was lovely. It was a very nice review. I wasn't expecting such depth of fission, and it was quite interesting for me to personally to see that. I think I will defer questions and let's see what we can come up with in terms of some hands raised or chat. Let's try the chat function. George Erickson. Oh, he doesn't have a mic symbol, so he's going to raise his hand. And somebody's replied to him, just raise your hand. So we'll try that. Okay, I've got, let's see, we'll continue to scroll. I'm not seeing any further. We'll try question and answer over here. That might work. There are no open questions. Okay. At the moment. So we'll just let things lie for a minute. I would like to, my comment on your talks are reflect perhaps some personal bias in that I have some reservations about these triso particles. I think the idea is good. This is where you have the very high temperature reactor.
Yes.
But when you look back at the history, it's been tried twice in Germany. And in one case, the spherical particles got stuck in the pipes. And in another case, I'm not sure what else happened, but in both cases, there was heating. It wasn't a true meltdown, as you point out. They're fairly well meltdown proof, but there was a high temperature reached, and they're still struggling in Germany to clean up the melted. There were some melted problems at the bottom of both chambers, and to the best of my knowledge, they have yet to clean up the residue that's radioactive in both of those places in Germany. So it has not contributed to Germany's satisfaction with fission. And it strikes me as a difficult way to recycle the spent fuel, because it's tied up in these ceramic particles, which have to be sent back to the manufacturer, and it's quite a tedious chore. Whereas with the thorium molten salt reactor, thorium fueled or thorium and uranium fueled molten salt reactor, I think those are easier to recycle. And also, in that, it's the recycling that is important to me, so that we don't have more waste accumulating. People are hung up about waste, and what I like about the Gen 4s eventually is that they will consume the waste that's sitting around in those casks. And so I would like to see more emphasis placed on recycling and on consuming the waste. So that's my criticism of the very high temperature fission reactors.
It is amazing to me that we have not solved the problem of, it's a political problem. It's not a physical problem, because you can make that Synrock, the ceramic discs with the fuel embedded in it, and it would be safe in salt mines for tens of thousands of years. But no governor wants to accept them. And of course, nowadays we're so badly divided. I can't imagine this issue coming up compared to all the other issues we have. The one thing, though, that recently we watched the film Chernobyl. It's the worst case scenario. And I think the worst case scenario is the fact that they weren't transparent with it. They kept it secret. It's the same thing with the pandemic. You have to be transparent when you have tragedies like this.
Indeed. I remember the time there were some brilliant bone marrow transplant people at the University of Washington in Seattle offered to help, and Russia did not want having Western people present, and they declined their offer to help. They may have saved some of the early workers with bone marrow transplants. So you're right, that was a problem. In Chernobyl, the other big problem was it's the only graphite reactor in Russia that did not have a containment dome. And so
exactly.
It was an accident waiting to happen.
That's right. That's right. Yeah. The containment dome is very important.
Yeah. Let's see if we have some, I see a couple of question and answers here. Lee asks, in the first slide, the space heating, 55.4% you said was electrical consumption, but did you mean overall energy consumption, since most residents in the country use natural gas for heating?
The amount of energy, the amount of electricity, electrical energy going to our everyday lives in the home. Those are residential. There are numbers for commercial, of course, but yeah, the 55.5 was, and it's natural, it's averaged over the country. Obviously, you need less in Florida, more in Wisconsin.
That's overall residential energy, is it not? That 55.4% is as a percentage of total residential energy consumption, not electrical specifically.
Actually, you're right.
That's what I was thinking, yeah.
Yeah, that's a good, thank you for bringing that up. I had a similar question, Lee. And Mert has a good question that's something you haven't touched on yet. Is there any radioactive waste or emission from fusion? I'm sure you have a good answer for that one. Bulent, go ahead on that.
Well, in principle, with fusion, you don't have any radioactive waste except some of the machine parts becoming radioactive. But there is no, in the DT fusion or the DD reaction, you have alpha particles, you have neutrons and protons, but you don't have any radioactive waste as such. So that's no problem. The amount of energy involved, 1 out of every 142 hydrogen atoms in the sea is deuterium. And there would be roughly 10 billion years worth of energy for a population of leveled off at 30 billion for the world. It's inexhaustible, obviously. So the better side of fusion is, 1, there's no radioactive waste. 2, there's no explosion possibility because it shuts off the minute it starts picking up impurities from the walls of the reactor. You have to keep the fuel absolutely pure for the fusion to take place. So it turns off itself. So that's the upside is obviously far, far greater than the downside, but it's that difficult to achieve. You can't you just can't scale up the machines. I've seen 4 generations of tokamaks at Princeton, from the first one, the Stellarator, through the TFTR. And each time they scaled it up a little bit, they found new problems. And that's what's going on with the JET in England and the ITER project in France. Right now, we seem to be on a nice course. If in 40 years ago, I would have said it'll take 15 years to break even, another 15 years to have commercial reactors. 15 years ago, I would have said exactly the same thing. It'll take 15 years for break even, 15 years to have commercial machines. Nowadays, we've come to the point where we can say by 2025, which is just in 4 years, we should break even. After that, I think it'll go fairly fast. It will be that 15-year period. So by 2040, we should have be in the grid.
That's nice. I'm glad to hear that. I've been waiting to hear that optimistic prediction, and thank you for that prediction.
I suspect fossil fuel companies who've opposed it because they want to sell as much of their product as possible will eventually own these machines. So, but until then, you're not going to get any support from them, certainly.
No. Well, I think there are so many negatives from fusion, from fission. I mean, largely, I think, hearkening back to the use of the bomb and the fact that fission was discovered on the way, in the direct way toward the bomb, to be in competition with what was imagined and to some degree reliably predicted to be research going on in Germany. And we were afraid that they would beat us to the draw. And so it was a discovery based and motivated by development of a bomb. And I think that's given it a really negative term. And when you add the few problems that we've had in Fukushima and in Chernobyl, and then the problems of so-called waste, which really is unspent fuel, but it's perceived by the public as a big hazard. And the cost of since Fukushima, the additional costs and time lags for construction, it's put fission in a difficult place. And I think fusion, at least, doesn't suffer from most of those. It only suffers from the fact that it's always 15 years away. And now we hear for the first time that to get a workable reactor might be only 4 years away, and another 15 after that. That's finally an improvement over 15 plus 15. So I'm glad to hear that.
Richard, I have a question about your solar electrical system. My son just had solar installed. How are you in the grid, and how does it work?
Yes, there are very few people who are off the grid, because to be off the grid, you have to have heating provided either by wood or by natural gas. And so there's only one individual I know of in the Madison area who's off the grid. Most of the people do go on the grid. And when I joined, 2 years after I put on solar panels, I applied to my electricity supplier, Alliant Energy, and I asked them if they had a grant, and they said yes. They would give me, there's a special thing going out to people to encourage solar panels. They would buy it back from you, from the generator at 25 cents a kilowatt hour. And we were paying between 10 and 15 cents, sometimes even under 10 cents, depending on time of day. So that allowed for the panels to pay for themselves in about the 10-year time of the contract, whereas it would have taken a good 20 years without that. So I happened to benefit by doing that at a time those contracts were available. I don't believe they're available anymore. but the cost of solar panels has gone down considerably. But when people say the cost, they only talk about the cost of the panels. They don't talk about the cost of the inverter, the installations. And if you want to really know what you're doing, you have to have an instrument that measures the accumulated energy before it goes back to the grid. And you have to pay for that. You can pay for it somewhat in its installation, but the Alliant Energy Company continues to bill you for its use and the information that you get from it. I mainly put on solar panels to learn from it, and so I paid willingly for that extra instrumentation. It comes to about $3 or $4 a month. So to get back to your question, there were 3 months this winter when my solar panels were totally quiet. I was not going to get up as I used to on a step ladder anymore and sweep them off. And so they just woke up a little over a week ago as the solar panels, and now they're generating about 6 or 7 kilowatt hours a day. Today they'll probably make 2 or 3 kilowatt hours. And so, as you know, those things cost. A kilowatt hour costs us about, depending upon your time of day arrangement, somewhere in the neighborhood of 15 cents. So it's not a big harvesting income. Some people, mine is a very small system. Some people install, instead of 2 kilowatts of energy, they install 3.5, 4, or even 5.5 kilowatts of panels, which involves a huge outlay of about $50,000 or so. But back in the old days, probably half that today.
Well, what would be the latitudes where it would be most optimum?
Yeah, California is a good place, in Florida, Arizona. I think the people talk about when there are maps of the United States showing the solar incidence, and Arizona and California tend to win out because you not only have the lower latitude, but you have clearer skies in general if they're not smoke laden, and as California has been lately. And so those are good places to have solar panels. But one of the things that solar has not dealt with in this country, they're starting to deal with it in Europe, is how to recycle the panels and the high consumption of rare earths in the manufacture of them. And people are just not even addressing the issue in this country that I'm aware of. They generally last about 20 years, and my panels are now 12 years old. So in 8 years, I'm going to have to think about whether I want to replace them. What do I want to do with the panels that I take off?
Right. The price of solar panels, though, must have come down a great deal.
Yes, they have. They
remember,
but as I mentioned, that's just the panel alone. You still have the installation costs and the inverter. That has not changed significantly.
Richard,
Right.
recently I checked to see what it would cost to buy solar panels for our house that would make most of the power that we need. It's going to be $75,000.
Okay.
And I said, I won't pay that much on energy for the rest of my life.
Now,
So, as much as I'd love to have solar panels that would make electricity for my house on my roof, it just doesn't really make a lot of sense to do that. I already have solar hot water, and they told me, and that's nice because we never run out of hot water, right? But they told me that the payback on that system was about 80 years.
Now, we're not talking hot water here. We're talking generally photovoltaic.
Yeah, but I'm just mentioning that that's the one kind of panels that I happen to have on my house.
At the moment.
Yes, at the moment. Yeah.
Oh, that's called passive solar. Yeah.
Right.
Yeah, I was thinking of doing that. I was going to have half of it passive and half photovoltaic. And they looked at the best place on my house to install them, and that was in the garage at the far end of the house. And so they thought that by the time the hot water circulated all the way to my water heater, it would be impractical and it would be much better to go photovoltaic.
Yeah.
Right.
Hey, I have another question. Okay, this is a philosophical question. It's just kind of a fun question because I like to hear what a physicist would say about this. Okay, so after the Big Bang, what forces would be sufficient to overcome entropy? Okay, and considering that entropy says that the entropy of the universe is constantly increasing, right? So after the Big Bang, which put chaos into everything, right? What would you have after that? Entropy takes over and you've got more and more chaos. So what brings this all back to make our complex bodies?
Wow.
Fun, huh?
Wow, this is something that I have to sit down and think about and write out.
That's okay.
Yeah, that's okay. Just you can write to us later and be fine. I'm just curious as to what your thought processes are that on that being a physicist.
So the
Yes,
question is,
yes.
again, after the Big Bang, what forces would be sufficient to overcome entropy, such that our terrifically complex bodies could be formed? And you can send that answer back to me, Bulent, and I'll pass it around to our group.
So Lee,
Okay, I'll do that.
Lee,
I
this is
have an answer, but I'll send it to you.
Lee, this is Doug Edwards.
Hi, Doug.
Hi, Doug.
Actually for Christmas, I got a book. The title of the book is The End of Everything. And I recommend that you read it because
What a pessimistic title.
goes through this isn't known now. It's all hypothetical and perhaps theoretical, but several different scenarios are examined that describe what ultimately happens in the universe. It's very, very interesting. Not terribly uplifting, but interesting nonetheless. And it's actually written by a physicist, an astrophysicist.
What's the name of the book again, Doug?
It's called The End of Everything.
The End of Everything.
In fact, I'll give you the name of the author in a second.
Yeah, okay.
Thanks, Doug. That's I'll have to look that up.
Well, did you like the book?
It's a great book.
It was. I'll look into it.
Very interesting.
Well,
Hold on a second. I'll find it.
Let's see if there's anything under chat. Anything under A10.
The author's name is Katie Mack.
Thank
what
you.
is it? I didn't understand. Who was the author? I'm sorry.
Her name is Katie Mack.
Okay.
M-A-C-K.
Yep, M-A-C-K.
Okay.
Yeah.
Very, very interesting book. Very interesting book.
And does she address that question, do you think, pretty well?
Actually, she goes through, I'm going to say it's 4 different scenarios. This is, I would say, current thinking among astrophysicists as to what will ultimately happen. And the time scales are on the order of hundreds of billions of years.
Right.
Okay.
Now, there's a book that I would recommend. I read recently, A Universe from Nothing by Lawrence Krauss.
A universe from nothing. Okay.
World Economic Forum in Davos.
Yeah.
Who was the author on that one again, please?
Krauss, Krauss.
Okay.
Lawrence Krauss.
Okay. Thank you.
and this is the answer to the question, don't you have to have something in the beginning? And according to Krauss, if energy is the energy of the universe ultimately is zero, it doesn't change. The energy of potential plus kinetic energy is zero.
Mhm.
And mathematically, it makes sense.
Right. I mean, if you consider the universe as a system, as a thermodynamic system, yeah, the
Yes.
change of energy by conservation of energy, the total change of energy in the universe has to be zero. That's correct.
That's right. Now, are you a physicist?
I'm a PhD chemical engineer.
Oh, okay.
That's why I think so weird.
That's not the only reason.
Well,
At
we're-
Caltech, there's Frances Arnold, who won the Nobel Prize in 2018 for her evolution-assisted, what is the system? Manufacturing new enzymes. And she's a chemical engineer. She runs the lab at Caltech. Something you might be interested in. And my advisor was Eugene Wigner, who was a chemical engineer to start with, but he became a physicist, of course.
Hmm.
Did you teach at the University of Wisconsin?
No. I worked for the U.S. Department of Energy in Morgantown for about 8 years, and then I got interested in electric vehicles and batteries, and so I'm kind of into those sort of things more recently.
Oh, practical things then.
Yeah.
Lee will be speaking to us about lithium-ion batteries, the history and the future of it, coming up in next month. I think late April, right, Lee?
Right. Yep. I've been working on it.
Well, just reminding Bulent, April the 19th.
Yes.
I have it right here. Battery development and recycling. That's wonderful.
Actually, the
Our title has been
thing
changed.
is lithium-ion batteries, past, present, and future, because it's also to cover a discovery conference by the Wisconsin Professional Engineers Society.
Hmm.
And people have to get PDH credits from it, so it's got to be a little technical, and it's also historical like yours is.
Yes, that should be very interesting. Do you have slides, or is this
Yeah, I'm working on slides. Yeah.
wonderful?
Now, next week, everyone, Bulent will return as our guest speaker, and he will talk from the perspective of art and a bit of science history on some of the geniuses in our that we have to be grateful for. And you can see some of the posters from articles in National Geographic on the wall behind Bulent to the left from his experience working with National Geographic. So we look forward to that immensely. And I was, when Bulent came and visited about 5 years ago, I felt that it was most appropriate if he talked to us about fusion. And so I asked him to speak to our friends, our neighbors and friends who came, and we had a little private basement slideshow. But this time, because of the simplicity of Zoom, Bulent has kindly offered to give his talk next week, even though it is not specifically pathways to a sustainable planet. It could be described as pathways to civilization and the creative genius involved in our civilization. And that's a very important part of our evolution as well. So I'm delighted that Bulent has agreed to give us a second lecture next Monday morning. So
Thank you
if
very
there are no
much.
further questions,
Okay.
feel free to ask them through me, and I can relay them to Bulent. And I appreciate everyone's attendance today and the questions. And we'll look forward to seeing you next week, Bulent.
Thank you very much. Wonderful to speak to all of you. Bye-bye.
Thank
Bye-bye
you.
now.
It was a great
It's a real,
presentation.
real pleasure. Thank you. Bye-bye.
Richard, did you notice that George Erickson needed to leave early, but he did ask if you would please send him Dr. Atalay's email address?
I'll do that. Thank you for passing that along.
Sure.
Thanks, Louise.